Davide Gabrielli. The title is here.
Okay. Thank you very much to the committee for the invitation to give this talk. So this is the title, and these are the. So I will present some results and I will give you a general discussion and some results. And these are the co-authors that I have to thank also for the result that I get. So I will discuss some models. This is the general framework where I'm working. I will discuss some model of non-equilibrium statistical mechanics. This means that there will be some fluxes, so there is matter or energy that is flowing across the system when is in the stationary states. More precisely, I will discuss some stochastic models that are not reversible. I will discuss variational problems. This is because I will use large deviations theory for studying my models, and this gives in a natural way some variational problems related to this. So, what is large deviations? This is just a formal definition at the beginning. So the general setting is that just a metric space where there is a function that is called the rate function, and for which these two bounds holds. But let's say that there is something to. No. So it will be enough, at least, also to understand at least the spirit of the talk. The last formula, that means that the probability that the random variable take this special value x is exponentially with this rate x. So this functional is positive, and there is the typical behavior where the rate function is 0, and then otherwise is strictly positive. This is the typical situation that you have. Examples are this. So the most simple example is this one. You take a sequence of Gaussian random variables where the exponent is multiplied by n. Then if you want to describe large deviation for this sequence of random variables, then okay, the rate function has this simple expression, and this gives exactly the intuitive meaning of large deviations. And a less trivial example that will be useful also in the following is a gas of independent coins. So I have a sequence of independent coins. If I have the result of a toss of a coin is just can be either 0 or 1, and every result is independent from the other. And so this is the situation, starting from my configuration of coins. I construct what is called the empirical measure. This is the definition, and this is the picture. So you just take the interval 0, 1, you consider a lattice of size 1 over n, and you put a delta measure with a mass that is equal to 1 over n in each point where you have, as a result of your when in the position where the coin had a 1, and nothing when you have 0. So this is a special configuration, and associated there is a combination of delta measures. So this is called the empirical measure. That will be, it will appear in also in the following. And this is a random positive measure on the interval 0, 1, and you can quite easily prove that a large deviation principle holds for this object. And so if you want to go to see which are the probability to see a kind of density profile for your empirical measure, then this is exponentially small, and the rate function is this integral here, where the special function here is the relative entropy. So here maybe is something. So you have to stress that. So the empirical measure is a random positive measure that is atomic, so has just delta components, but the rate function is different from plus infinite only on absolutely continuous measure. So you see just and another tip. So another things that another observation that can be useful is that so this rate function is always positive and is 0 when rho is the constant measure with a constant density that is equal to m, and m is the parameter of my coin. So m is the probability to see a 1 in each when I throw one single coin. Then you have variational problem when you are describing fluctuation of a system using large deviation. You have some variational problems, essentially because so there is this general principle that is the contraction principle. So if I want to see, I just described which are the fluctuation of the empirical measure, but then let us suppose that I am interested just on the number of 1 that I saw in my experiment. So I have just to, so the average number of 1, on the left hand side there is the average number of 1, and this corresponds with my definition of empirical measure just on the total mass of my measure, on my empirical measure. Then this general principle says that if you are interested just on the average number of 1, then this satisfies also a large deviation principle. So the probability to see a given value is exponentially small, unless it is the typical one, and the rate of exponential decay is obtained by contraction, solving this variational problem here. So you have to minimize among all the density rho that have this fixed total mass, and you get the rate function for this other random variable. So which is the simplest non-equilibrium model is just we consider just a continuous time Markov chain on a finite set. So this is called usually continuous time Markov chain with exponentially small rate of transition. The name comes from usually this problem is discussed at discrete time. In this case, the probability transition are really exponentially small. Here, the transition rates can be also exponentially big because this big R can be either positive or negative. So, but this is the general framework. You have a finite set, you have a continuous time Markov chain, and the rate of transition, so that measure the tendency to jump from one side to the other, depends on this parameter n in this fixed rule that is there. Then this is a combinatorial result. So there is a combinatorial representation of the invariant measure. The invariant measure is I let my Markov chain evolve for a given time. If the time is big enough, I go to see the probability to be in a fixed point. This probability will be distributed according to the invariant measure. So the invariant measure has this combinatorial representation. There is a sum on a class of graphs that I will illustrate now. And then there is a product on all the edges of the graph of the rate Rn. And then there is a normalization factor that is, I call it just zeta of n. So the class on graph on which I have to sum are essentially oriented trees that are oriented toward the fixed point x. So x is the point where I'm computing the invariant measure. I have to sum on all oriented trees that are oriented toward the fixed point x. I have to do the product on all the edges. I divide by 1 over Zn, that is just a normalization factor, and this is the invariant measure. So it's this is essentially, I think is due to Frieden and Wenzel, or maybe it's also older. To check that this is the invariant measure is quite easy. You have to put, once that you have this representation, you put this representation on the stationary equation, and you get the equality among two combinatorial objects that are graphs like this that have one single cycle. So it's just you have to try to put this in the in the stationary equation, and you get an equality among combinatorial objects. So this is the class of graphs there. So for this, then for this non-equilibrium model, there is a simple way to know that the invariant measure will satisfy a large deviation principle, because you see, is obtained as a sum of product of objects that are exponentially small or big. They are always small because there is the normalization factor here. And then to get the exponential rate of decay of a single point in the invariant measure, you have to minimize. So you have to go to consider which is the minimum spanning tree, and with the associated this weight here. There is a constant there, but okay. So in general, this is a hard problem. Also, if you're in a finite graph, is not so easy to construct it, so to solve it. And it's the first example where you have a relation among the large deviation for a static large deviation, so the large deviation for the invariant measure, that is the W, this is the large deviation for the invariant measure. You get this rate function in terms of the large deviations for the rate, for the dynamic one. So it's the simplest case where this happens. If you are choosing the rates in such a way that the model is reversible, because you can do this, for example, this is a choice where the rates are reversible, then indeed you can solve this problem. Also in this case it's not completely elementary, but you think a little bit and you can solve it, and you get that this W indeed coincides with the function h. So in the reversible case is easy. In the non-reversible case, you have to solve a combinatorial problem that can be quite hard. So, okay, this is the general situation. When you are in non-equilibrium, you have several phenomena that can happen, several strange phenomena, and the aim of this talk is exactly this. In general, you have some very different phenomenology associated to the non-equilibrium statistical mechanics, but there are some few cases in which you can solve exactly the problems like this, and you get some geometric construction that can be interesting, I hope. So this is the Frieden-Wenzel theory, is a result that is in the spirit that of the slides before. So let us discuss this in a concrete framework of a stochastic differential equation. So there is you have a differential equation with a vector field that is B, and is perturbed by a white noise. Then there is a dynamic large deviation principle. So if you are going to see which are the path of this stochastic differential equation, and you want to see which is the probability that they are near to a fixed trajectory small x on a fixed time window of t1, t2, then this probability is exponentially small with a rate function that is this square of, so it's essentially is a measure of on how much the equation without the noise is violated. Then what happens in a special case when B is a globally attractive vector field, so as a unique equilibrium point, and starting from any point you are converging to this unique equilibrium point, then the invariant measure for this stochastic differential equation will satisfy a large deviation principle also on epsilon, that is a parameter, and the rate function is called the quasipotential. This is the representation here. So as a variational representation that is written in terms of the dynamic one. So this is another formula that connected the static large deviation principle, that is V, that is the quasipotential, with the dynamic one, that is the rate E, that appears in the formula above. So you have to minimize on all the trajectory that you have to minimize on the time window t, and all the trajectory that at time minus t are in the equilibrium point, and at time 0 are in the fixed point x. So this is the geometric situation. X, you have to remember that is the unique equilibrium point of the equation without the noise, And so in red, if you consider the equation without the noise, with the initial condition x, so the orbit of the system will follow the red arrow. Then the quasipotential says that to compute the quasipotential in the position x, you have to minimize on all the path that exit goes not from x to x bar, but goes from x bar to x. Okay, so the green one will be one of them, but one of them could be just to reverse the typical relaxation path. Indeed, the inversion of the typical relaxation path is what happens in the reversible case, in the equilibrium. In the non-reversible case, you have a different trajectory that in general it's very difficult to compute, but I will show at least one example where it's possible to an infinite dimensional example where it's possible to identify exactly this trajectory. So this is indeed the picture for the stochastic differential equation, but you can think this in an abstract way. So you can think also this geometric picture can be also in an infinite dimensional framework. So the quasipotential, if the stochastic differential equation is reversible, this means that the vector field B is a gradient, then you can compute the quasipotential that is strictly related to this function S, it's just by a factor 2. In general, if the system is not reversible, the quasipotential will be not differentiable, because you have situation like this. So you have a curve that is called the caustic, and it's such that if you can have two points, x1 and x2, that are very near, but on opposite side of this caustic, and for which the minimization path will be very different. And this gives exactly a structure of differentiability of the quasipotential. And this situation, indeed, we can really prove for a model that is the weakly asymmetric simple exclusion process. I will say something about this probably later. So this, and in general, so when V is not differentiable, it's very difficult to find example where you can really give an explicit expression for this quasipotential V. And I will show one example where this is obtained by a geometric construction. In general, so the situation of the quasipotential like this is, you have to recall that is when the vector field B has a unique equilibrium point, and this is a stable one. In general, you can have a vector field that has several stable equilibria. You can have also a stable closed orbits. Then to compute the quasipotential, you have to do the following. You have to consider every single equilibrium point as a point of you have to construct before a Markov chain, a Markov chain with exponentially more small rate transition that goes from the single equilibrium point. So you have to solve a combinatorial problem, the same combinatorial problem that I showed before in the case of discrete. So before to fix the W, you have to solve a combinatorial problem like this, where the weight R are given by the problem, and this fixes some W associated to each single stable equilibrium point, and then from any stable equilibrium point, you have to find the optimal path that go to X, and you have to minimize all of them. So this is this is a very hard combinatorial there is a very hard combinatorial problem, and then you have to minimize on all this. In general, this is very difficult to is very difficult to solve in general, but then there is an example, an elementary one, where this indeed is possible, and it's so it's the simplest situation, obviously. So it's very simple problem where you have a stochastic differential equation on the unit circle. So essentially, you have to think this B as a periodic function of period 1. And then you have to compute this S, that is the up to a factor 2, is the primitive of the vector field B. Then you are on the unit circle, and then what happens? If S is periodic, this means exactly that the total integral on 0, 1 of the vector field B is identically 0, then the system is reversible, and the quasipotential for the invariant measure it coincides with S. But if this relation is violated, then you have that your process is no more reversible, and for example, you can have a constant vector field. This indeed is a more general situation, and the process is no more reversible, and this function S cannot coincide with the quasipotential, because the quasipotential is a function that is defined on the unit circle, so it has to be periodic of period 1, and S is not periodic of period 1. So what happens in this situation is exactly that you get a quasipotential that is not differentiable and has some flat parts, and you can get this result in two ways. One, because the situation is so simple that you can compute the invariant measure and study with a kind of Laplace-Varadan theorem directly the stationary states. The other approach that is not so strict is that you can really solve exactly the combinatorial problem and the quasipotential. So this is not hard. And the solution is this. So in black you have S, but remember we are in not periodic, in not reversible situation. So there is an external field that is E that goes that way. So S is not periodic, at 0 is 0, but R1 is strictly positive. So S cannot be the quasipotential. Then you do what is called the sunshine transformation. You are at the sunshine, and so the light is arriving in a horizontal way from the left. The light is arriving from the left because the vector field goes that way there. Then you have to think of the graph of S as a mountain profile. So this is a mountain and valley. Light is arriving, and there are some part of the graph that are in the shadow, and some part that are enlightened by the sun. Then what you have to do, the construction is like this. The parts that are in the shadow you keep intact, so you keep as they are, and in the part where there is the light, you put instead a flat part, a constant part, and then you glue all together in such a way to have a continuous function. The function that you get V is a periodic function, and is a periodic function of period 1. No? This construction works always. Also, if you are in the reversible situation when the S is periodic, because in this case you can, if you think a little bit, all the graph will be in the shadow, and so it will be intact. If the vector field is strong enough, then all the profile will be in the light, and the rate function will be constant and flat. So this transformation covers all the possible situations. Another exactly solvable variational problems that we get from non-equilibrium statistical mechanics is given by comes out from the study of stochastic interacting particle systems. This is a special stochastic interacting particle system that is called the boundary-driven one-dimensional simple exclusion process. So there is a lattice. Particles can stay only on the lattice. They do a continuous time Markov process, and the dynamics is the following. On each lattice side, there can be at most one particle, and every particle try to do a simple symmetric random walk. So particles that have free both the left and the right side, they can jump with the unit rate and with equal probability to one of the two sides. But here, where you have that particles are, there are two particles that are near. If the particle on the left try to jump on the right, this jump is not permitted because you cannot have two particles. So the jumps that are violating the constraint of one single particle for sight are violated. Particles that are at the boundary, so on the right one, the particle can either jump to the left and continues, and then she can continue to his random walk, or jumps to the right and then disappears. At the boundary, there are some creation of particles. So on the left boundary, I am creating particle with a rate that is R0, and on the right boundary, I'm creating particles with a rate that is R1. So this, for example, is a model for heat conduction. Could be heat conduction on a one-dimensional object. And if the rate R0 are different from R1, this one-dimensional object is put in contact with two different reservoirs at two different temperatures. So when R0 is different from R1, the model is a non-equilibrium model. When R0 is equal to R1, I put in contact with the two sources that are at the same temperature, and then the model is an equilibrium model and a reversible model. Not really temperature, so it's just, yes, it's density, just an interpretation. It's well, this is essentially the density. The rate of creation will create different densities. Then this process has a non-trivial limit in the diffusive rescaling, so you have to accelerate. Every particle was trying to jump with a unitary rate, then you have to put n, that is a parameter of your model, that is n is exactly the number of lattice sites that I have here. So you have to accelerate my process to see a non-trivial behavior. I have to consider the empirical measure, pi n. No? Here, essentially, you can think of particles as a configuration of 0, 1, and associated to configuration of 0, 1, you can associate this object that was called the empirical measure, that is a positive random measure on the interval 0, 1. And you can prove that this system here has a hydrodynamic scaling limit, so the limit, this empirical measure at time t will converge to a measure that is absolutely continuous with respect to the bag, and is obtained as the solution of the heat equation with fixed boundaries on the density. These densities are a function of the rate R0 and R1. So you have to solve this one-dimensional heat equation with the fixed boundary, and you get the limit when the limit that you get. So here we are in an infinite dimensional situation, but the general strategy is like the one for the Freidin-Wenzel situation in the stochastic differential equation. So you can ask now to see which is the probability to see in a given time window a given density profile rho xt, and this probability will be exponentially small with a rate function that is obtained like this. So it's a norm of an external field H that you have to put on your equation in such a way that to see the rho that is different from the typical one. So I don't know if it's clear. For example, if rho here it's the solution of the heat equation, the external field H that I have to choose here is identically 0 because it is exactly a solution of the heat equation, and this indeed is the typical situation, and it's okay. If I take a density profile that is different from the typical one, I have to put an H that is different from 0, and the rate function, the exponential probability of this density profile will be related to this special norm of the gradient of the external field. So this is a dynamic large deviation, and if you are interested in the large deviation for the empirical measure, when the particles are distributed according to the invariant measure, you can compute the quasipotential, but has exactly the same variational characterization as in the finite dimensional case. You have to minimize on all the trajectory that exit from the equilibrium. What is the equilibrium in this case? The equilibrium will be the unique stationary solution of this heat equation. We are exactly in the case of a globally attractive dynamical system, infinite dimensional, as a unique stationary solution and is globally attractive. Now, if R0 is equal to R1, the model is a equilibrium model, the system is reversible, you can exactly get the invariant measure that indeed is a product measure, and essentially your particles are distributed like a gas of independent coins. When R0 is different from R1, the model is not reversible. What you get is that in the system appears a long-range correlation, and the rate function has this expression. So if you want to compute the rate function for a density profile rho, you have to compute this integral here, where the function f is obtained as the unique increasing solution of, so if let's suppose that rho R0 is less than rho R1, then f has to be increasing, has to solve this second order differential equation. So here you have this long range correlation appears here because this f that you have computed is global and depend globally on the structure of the rho. So, okay, it has a very different structure with respect to the case of independent coins. And so now, how do you compute this quasipotential? You can solve it using an infinite dimensional, at least formally, an infinite dimensional Hamilton-Jacobi equation. Otherwise, you can, let's say, you can identify exactly which is this green path that goes from the equilibrium to x. You can exactly identify it. This is one of the few cases when this is possible. And in principle, you have to solve the coupled differential problem that is above. That seems quite difficult because you have to solve this partial differential equation for rho, where rho is related, where appears also f, and f is related to rho by this equation here. But if you do some computation, indeed, and sometimes this is called the magic transformation because this seems really very hard to solve, but it happens that this problem here is indeed equivalent to this problem here. So you have a fixed rho 0, you have, how do you proceed? You have just to solve this, you give me rho 0, I put rho 0 here, you have to solve this second order differential equation. This gives to me the initial data for this f here. I solve the heat equation. Once that I solve the heat equation, I put my solution here and just have to compute some derivatives to give the rho. And I can get the rho. In particular, using this equivalence of these two problems here, you can prove that indeed this is a good path that you have to do indeed the time reversal of this. This is defined from in the time interval 0 plus infinite. The minimization path goes from minus infinity to 0. For example, using this transformation here, you can prove that in the limit when t goes to plus infinite, this rho that you get from this solution will converge to the rho bar that is the unique equilibrium point. So this is another variational problem in non-equilibrium statistical mechanics, where you can really get an exact solution. And I would like to discuss a final example where you have a very complicated stationary state and model, but when you can really get an exact solution and using also different techniques. This is a model that is called a two-class totally asymmetric simple exclusion process. So you have particles that are red and green. The red particles are first-class particles, so that they are more important than the other. The green one are second class. So now a single particle, both first and second class, try to do not a simple symmetric random walk, but a random walk, so every particle can jump only to the left in a anti-clockwise way. So a red particle isolated, wait an exponential times, then jumps to the right, and so in the same way, the same behavior as the green particle, wait an exponential times, and then if the lattice in front of R is empty, she jumps on these lattice sides. On each lattice side there can be at most one particle, so this particle here cannot jump here, so there is no stochastic clocks because it's occupied, and this particle can jump only if this particle before jumps, and this because both have the same class. But here you have a special situation. There is a red particle that is first class and a particle, a green one, that is second class. So this particle wants to jump there, and she is first class, the other one is second class, and then she can do. So this particle with the rate 1 can jump there, and then the second class particle has to jump backward and take, so in this case the red goes there and the green goes there. So first class particle can go only clockwise, anti-clockwise, but the green one, they try to go also only anti-clockwise, but sometimes they have to go in clockwise direction because by priority reason. So this is the model. Continuous time Markov chain when there is on a ring, on a one-dimensional ring. So it turns out that the invariant measure for this process is quite complicated. There are several representations of this invariant measure. There is one due to Derrida using the matrix representation that is quite complicated. By a few years ago, there was a very beautiful representation of the invariant measure of the process that is due to Omar Angel. So if you like combinatorics, this is a very, very beautiful paper, very elegant. The invariant measure is like this. So now we have red particles that are the first class particles, essentially. Not immediately, but they will be first class particle. And there are blue particles. Blue particles here you have to think as total particles. So in particular, the number of blue particles is bigger than the number of red. So this is the invariant measure for a two-class TASEP that has 6 first-class particles and a number of second-class particles that is exactly the difference among the number of blue and the number of red. So the total number of particles in a model coincide exactly with the number of blue particles. Then what I have to do? I have to generate samples of red particles and blue particles in an independent way. So these particles here are distributed independently. The red ones are uniformly distributed among all the possible configurations, and the blue ones are distributed uniformly among all the possible configurations, and the distribution of red and blue are independent. Then I have to, this is a realization of my configuration of particles. Then starting from this configuration of particles, I have to do what is called the collapsing procedure. Then I have to give some labels to the red particles. There is particle 1, 2, 3, 4, 5, 6. But this is you can choose as you want. The result will be independent on the labels. And then you have to start from the first particle that you have to move in a clockwise way. Remember that before the particle was trying to go in the anti-clockwise. You have to move. Now, a red particle has to be in a place where there is also a blue one. The number of blue is bigger than the number of red, then this is always possible. So particle 1 tries to go in a clockwise way up to the first time that find a blue particles, but has not the red particles there. So the first one is here, but there is also already a red particle there, then has to go to the next one. So these red particles at the end of the collapsing procedure will end here. This particle number 2, it has already a blue particle above, and then she stays here. This one has to move, this is already occupied, and that one is free and goes there. Then the 4, it's okay, the 5 move here and goes here, the 6 is okay, and the collapsing procedure is finished. So now, what do you do? At the end of the collapsing procedure, you will have just a situation, you will have empty sites that will be empty sites. Lattice sites where there is the situation above, and when the situation is like this, you put a first class particles there. When the situation is like this, you put a second class particles there. Now, the result that you will obtain will be a random configuration of particles that is very far to be independent because it has been constructed by this algorithmic construction. And if you do this identification, the distribution will be exactly coinciding with the invariant measure with respect to the two-class TASEP. And so essentially what you are, okay. So is exactly this. You have a pair of configuration of particles that is eta tilde 1 and eta tilde t. T is for total because you have to remember that this means the total number. The sum of the particles 1 is less than the sum of the total particle. From this pair here, using the collapsing procedure, I go to construct a new configuration of particle n1 and t. That is, I call it the collapsed configuration of particles. Then what you can prove about this construction is that the result is independent on the label that you give to the particle. And if you are sitting on a bond, you are sitting just on a bond of this ring, and you go to count the number of red particles that are passing through it, you get an expression like this, a supremum, and this is a sum on all the intervals that are suitably oriented with respect to the flux that you have, and this is a positive part. Okay, then what happens is that this is an algorithmic construction that gives a transformation of particles, but indeed using exactly this formula for the flux, you can generalize to this collapsing procedure not only to configuration of particles, so now you can completely forget about the algorithm, but you can generalize this construction to abstract positive measure. Then you have a pair of positive measure on the unitary circle that satisfies, so the mass of the first is less than the mass of the total. Then you can define this collapsing procedure, and this collapsing procedure will take, so the rho t will coincide with the rho tilde t, and this is the definition. So the collapsed measure rho 1 will be defined by this, where the flux across one single point x is defined like this. And you can prove that this is a good definition and gives, you start with a couple of positive measure, you end with a couple of positive measure. And indeed, this formula here gives exactly is a formula that gives exactly the transportation of mass in a clockwise way. So this is how it works. So let us show how it works, this transformation of mass for two absolutely continuous measures. So the red one is rho tilde 1, and the blue one is rho tilde total. So you have two density profile. The collapsing procedure, what is doing is keeping this mass with the light green, and is moving to the right, in a clockwise. If you are thinking on the torus, to the right, it goes there. At the end of this collapsing procedure, the density profile of the measure rho will be like this. So untouched up to this point. Then here we will follow the blue one up to here, and then we'll go back to the red one. So this is a kind of mass transportation, the minimal mass transportation, the way in which you can transform a measure into another one in a minimal way, moving mass in one direction. And then with this general construction, then you can you can solve using the combinatorial representation of the invariant measure. Indeed, you can solve the problem of finding the large deviation for the invariant measure for this non-equilibrium model. Why? Because you can use contraction principle. So you do before large deviation for the variable with the tilde that was constructed in an independent way. So you get a kind of rate function given by a kind of independent coins. Also, if these are not Bernoulli but are uniform, so there is a constraint of total mass fixed, but let us forget about this. And then you can get the large deviation for the stationary non-equilibrium state for the distribution of the particle just doing a minimization. So you have to minimize this rate function here on all the pair of measure rho tilde such that they are collapsed. With this collapsing procedure, they are collapsed to the pair rho 1 and rho t that you are interested. And it means that this variational problem, you can exactly solve it and coincide with this expression here, where this rho 1 hat has to be computed that way. So there will be, you have to solve at most countable variational problems on each interval where the density of rho 1 is coinciding with the density of rho t. So take an interval where rho 1 is equal to rho t. Then the density profile that appears here is obtained in such a way that its distribution function on that interval is exactly the concave envelope of the distribution function of the rho 1. So this construction here gives also in this case some long-range correlation, because you have to do this concave envelope construction, and also the rate function that you get is not convex. So this means that there is a kind of instability of in the system in the rate function. And that's also my 3 examples are finished. Okay, thank you.